Hello everyone, this is Venkatesan, Master Student from IIC Bangalore. Today we are going to see about evaluation, my research work, which is the evaluation of dual stack analysis. So, what is MPTCP? Have you ever walked out of your house while on a call and the audio completely drops out for a few seconds before switching to the cellular data? This is the exact problem MPTCP or multipath TCP was built to solve. So MPTCP operates at the transport layer, allowing a single connection to seamlessly use multiple paths like Wi-Fi and cellular simultaneously. To the application, it looks like a standard single path TCP connection, but under the hood, MPTCP manages multiple subflows. But what happens when one of those subflows abruptly fails? Does the system instantly recover or is there a hidden cost? In this research, we dive deep into the empirical and mathematical realities of MPTCP recovery cycles. So this is our system model. Here we are using dual Wi-Fi system setup. So we have two systems, one which act as a server, the other one is act as a client. Here the client is connected with two access points using two separate Wi-Fi NICs, and then at the back end these access points are connected with the server through the internet. There are two main parameters in the MPTCP operation. One is reinjection time that we are going to define now. The other one is recovery time that we will define later. So what is meant by reinjection time? Let's consider we have two subflows. Each contains the traffic simultaneously. In our example, the data packets D1 to D8 is scheduled on the first subflow, and then D4 to D5 is on the D4 to D7 is on the subflow 2. At some random point in time, let's say the timestamp is T off, we introduce the loss at the subflow 2. So what will happen? The MPTCP did some work and then it will take all the packets which is stuck at the dead subflow. In our case it is D6 and then D7. It re-injected the packet into the other active subflow. In our case it's subflow 1. This mechanism or this event we mentioned as a re-injection time. So how do we measure that one? Okay, in our case T of is the timestamp at which we introduce the last at the subflow 2. TAC is the timestamp at which the acknowledgement for the last successfully received packet on the failed subflow, in our case that is subflow 2, is received on the other active subflow. T received is the timestamp at which all the non-transmitted segments from that dead subflow is successfully re-injected onto the active subflow. The absolute time difference between TRX to the TAC is the re-injection time. Next one, we'll define what is recovery time. The same example, here we have two subflows, but the subflow 2 was off for some time. So at the timestamp of T on, the subflow was brought up. What after that what it will do? It will start to transmit whatever the packets which is stuck at its buffer. In our case that is packet D6. That timestamp we referred as T data hold. After some point in time, once it completely transferred all the you know stacked packet on that subflow, it started to transfer the new data packets. In our case that is T12. That timestamp we referred as T new. So the absolute time difference between the data T new time to the data T old time is the T recovery time. We are evaluating our T reinjection time. So in our evaluation, we define the T reinjection time as phi plus k times the RTO. Here phi is the phase offset. What is phase offset? We'll see in a bit. So K is the number of times this MPTC watchman wakes up before the reinjection event happen. And then R2 is the retransmission timeout. We model the K as a Poisson distribution with the parameter lambda. So the loss is induced at some random point in time. So the time at which we introduce the loss, let's say that is the T off. So the time difference between the T off to the next RTO cycle, whenever this MPTCP watchman wakes up, that time we refer as phi. That is the phase offset time. So here is the proof for our evaluation model. Here we are comparing our evaluation model with the experimental data. So how do we do the experiment? So we have dual Wi-Fi setup as we discussed in the system model. In that, we introduce some rate limit on both the subflows at 5 Mbps, and then we introduce the 100% loss rate on one subflow, in our case that is subflow 2. So for 10 seconds we introduced or we turned off that subflow 2, and then for 20 seconds we turn on that subflow. So the total time duration for one on off cycle is 30 seconds. Like that we'll perform 100 on off cycles. So we gather the experimental data and then we fit our evaluation model to see whether the model follows the data or not. So this is what we got from our reinjection model. So it is as accurate as possible. Now we are going to do the evaluation model for the recovery time. So in our definition, the recovery time math model is the summation of drain time plus n loss times the RTO. Here what do we mean by drain time? The time the subflow is taking to successfully transferred all the buffered packet or the previously stuck packet once after it was brought up. So n loss is the uh, RTO penalty that subflow made to suffer. So this is the proof that our evaluation model which closely follows the empirical or the experimental data. Here also the setup and then the experimental data is, the experimental setup is same as like the reinjection model. Here this from this plot we can clearly say that our evaluation model closely follows the empirical data. So now we'll do the complete comparison between the experimental reinjection time and then our evaluation models predicted reinjection time. So here we are comparing the empirical CDF of both the things. Here on the x-axis we have time and then the y-axis we have the empirical CDF. So the solid one, the solid lines are the representations of the empirical CDF of the experimental data. The red one is for the 100% loss rate case, green one is for the 75% and then the blue one is for the 50% loss rate. All the the dashed lines represents the empirical CDF that we uh, expect that we got from our evolution model, which means our mathematical model. From this plot we can easily say that our evolution model successfully predicted the empirical data. The same goes for the recovery time. The setup and then the model, everything is same. From this plot we can easily conclude that our evolution model closely predicted the behavior of the real world experimental data for the recovery time and then the reinjection time. So with that, I'll close this presentation. Thank you for your time.